Alright, time for another draftphysics.com, debatephysics.com also. Video presentation. So it's a Neil deGrasse Tyson video on energy. So I figured I'll use it as an opportunity just to demonstrate that, yes, the conventional physicists just slander and lie about Newton. And they pretend that somehow this is Newtonian physics and that somehow they are in agreement with Galileo, Descartes, and Newton about how the universe functions, when they have a completely different notion. And I think all of those characters wouldn't fall for, this non-dimensional, whatever, you know, duality verse where everything is more than one thing and nothing is real or in any real place or doing a real thing. Kind of crap. All right, so leave us play the video and find the points where he just makes crap up and says shit about Newton that isn't true.
Chuck, another explainer.
So this video was titled, What is Energy? Neil deGrasse Tyson explains. Dun, 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 dun. I don't think so.
Okay.
Is bubbling up within me.
Ah.
Okay.
All right. Now, you sure that that's an explainer?
Or I gotta go to the bathroom. Is that what you're
Yeah,
saying?
I was going to say, what you have for lunch? 'Cause,
God, I just hate this planet. I just hate it. Hate it. Hate it. Just hate it here. Hate it. This clowniverse.
So I was just thinking
Oh, I hope you didn't hurt yourself.
how much we take for granted about when we use the word energy.
Yes, how much bullshit there is tied in this whole conversation when Descartes, sort of, 500 years ago, kind of got the first clue and kind of described it as, hey, guess what? This whole thing could have just been started like a machine, and the energy's just moving from one place to another place to another place to another place, and that's all that's really happening. Motion is just being exchanged between this object and some other object and then some other object, and it's just moving between big things and little things, and then from little things into big things. And you just lost all sight of that simplicity.
And it has profound origins. I mean, our understanding of energy has profound origins.
So, this is just the funny part, right? When the origins are all lies, okay, about what the actual history is and what these people believed. Newton was a strict and passionate dimensional, realitist, solidist, materialist. Okay, he believed that the distance between objects was real distance. It wasn't fake distance. It wasn't imaginary distance. And he believed that time was just a continuum. Okay, that's how long it took things to move from one place to another. Period. Not complicated at all, and in my opinion, perfectly simple. In the sense that it's just too true. You shouldn't even have to explain this to people.
The brilliance of Isaac Newton, who,
So this is the big joke, okay? The brilliance of Isaac Newton is saying there is no time dimension. There is no fourth dimension. There's three physical dimensions in space, and everything interacts in those three dimensions of space. The space is real. There is absolute motion in the universe, not imaginary framed motions. There isn't any way to change your perspective, okay, and change the universe. Things do happen simultaneously at the same time in two different places. It's the same time. The light we're seeing from the stars, Newton understood it took it a while to get to him.
discovered the laws of optics and gravity and motion and invented.
And right, and you ignore his laws of motion. So one of his fundamental laws of motion is twice the force, twice the velocity, 3 times the force, 3 times the velocity. Your elemental, most fundamental squared c squared function is a complete denial of Newton, a complete insult to his physics, to all his observations, to the Newton's cradle you're showing. You're basically saying it's Newton was a liar. No, he wasn't. He had it right.
The calculus.
You know, it's just, all right, brief interruption. So I don't know what all this, non-math on the board is. Let's pretend the pretense of complications.
Energy was not a fully developed concept in his time.
So it certainly was. So they all called it quantity of motion. They all knew it was something, and they thought of it as fluid. They thought of it lots of different ways, trying to explain the fact that it just seems to move from one thing to another thing, and that's what they were all figuring out. So at Newton's time, that's when they figured that part out, is in that whatever 100 years period, 50 years before Newton, 50 years after Newton. That was pretty much one of the big ideas.
And so I just want to sort of spend a few minutes offering an appreciation for a triumph of the human intellect.
So this is the tragedy, right? I mean, he's saying the triumph is Leibnizian mechanics, not Newton's mechanics. So he's overtly rejecting Newton's mechanics. He's not paying any attention to what the second law says. His whole concept of energy, all of the 400 or 500 extra particles they have created, are all based on these calculations made with mv squared, not with mv, okay? Not with Newton's mechanics, with their mechanics, Leibnizian mechanics. It doesn't have anything to do with what Newton would conclude to be a truth.
To figure out what the hell energy is, and then how to manufacture it and exploit it. I just want to spend a few minutes. This is like a...
So this has nothing to do with Newton either. Newton couldn't care less about exploiting anything, couldn't care less about its value to mankind. He just cared about trying to figure out how it works. That's it. He was just somebody, he was a really good mechanic, you could argue, he was really good at, say, here's the puzzle, solve the puzzle. All right, that was his objective, is to find the truth, how it worked. All right, and the fact is, in gravity, he basically said, look, this is what it does, and this is as far as I can go, because I don't have a sufficient microscope. I can't see gravity, so I can't tell you how it's manifesting the function. All I can tell you is this is what it does, and clearly something is doing it, and that's what he basically also said. It would be kind of silly to say nothing's doing it. Something's doing it. I just can't tell you what the something is.
Public service announcement for energy
Nice.
out there.
Yeah. One way to exploit it is call someone Sleepy Joe. Low energy, very low energy.
So this is necessary in a physics discussion, this whatever comic relief crap. Fuck. Yeah, the world has just gone to shit.
Low energy. So, energy is not a thing, right? You can say a rock is a thing and you can point to it. Or...
All right, so this is a conceptual difference. Again, that's, the physics was basically saying to people that, yes, the energy must be a thing because it is migrated from thing to thing. It's transferred. All right, and they were getting a glimmer of that in the idea of the photons, right? This invisible stuff flies through the ether, flies through space, or flies through a transparent atmosphere, hits things, and causes them to gain some energy, some heat. So it's obviously something that is a something. It's not a nothing.
Our planet is a thing. And energy is not a thing.
All right, so right there, that's not Newton's physics, and certainly it's not my physics, okay? I'd argue that, yes, of course it is a thing. The forces are actually discrete bits of momentum. All of the forces transfer momentum. It's because they're real things. They're just really small things. Particles can look like waves. Waves don't look like particles. It's really that simple.
So it was delayed in our ability to understand what it was and how to think about it.
So one minute they did all this great work and discovered it, and the next minute, everything's delayed and they couldn't figure out anything. Well, that is sort of the truth, okay? The fact is they just piecemealed this rubbish together. They didn't really have hard evidence demonstrating anything, and they just decided to formulate mathematics, okay, that was internally consistent but didn't have anything real in it.
So we knew some things. For example, when you had a cannon, back when cannons were like a popular tool in warfare.
Right.
So again, you wonder who these videos are for, you know, I mean, shit. You know, you have to explain what a cannon is.
There were physicists at the time who said, I have a cannonball.
All right, there weren't physicists at the time. There was Newton. Okay, this is Newton's analogy, right? So this is Newton explaining, okay, this revelation that the force of gravity, okay, is the same thing holding the moon up. So this is all Newton. This wasn't somebody else's idea.
And have this gunpowder, and the cannon is made of iron. Then I fire it, and if I keep doing this, the cannon gets hotter and hotter.
Okay, so that's much later. So sorry, he's going somewhere else. I thought he was making the gravity argument. Yeah, and the expectation is what? The explosion goes in both directions. The cannon isn't allowed to move. Generally speaking, it's blocked from gaining velocity. So where's the energy got to go? The explosion's pushing energy in all directions. Little bits of crap are flying out of the explosion. They're hitting the cannon on all sides that are exposed. And yes, some of that energy hits the cannonball. And the fact that the cannonball can move, all right, means that a portion of the energy is going to go that way, because that way is the only way to go. It's the only place that's yielding.
Well, where's that heat coming from? So what is it?
The explosion. Jesus, it's really that hard to figure this out. Is it really that hard? All right, so this is another example, right? Because the real thing that happened with cannons and heat wasn't the surprise that the cannon got hot. The surprise was that when somebody was boring a cannon, okay, it got hot. That was the part that they found difficult to understand.
And so in the urge to turn energy into a thing, early ideas was that energy was a fluid, was a thing that could move in and out of objects.
So, the truth is that it actually is a thing. Like an X-ray can go right through you. It really is doing it. The rays of the stuff are actually going through you. They're actually moving through you. So it is a stuff. And the real point is if the stuff gets stuck, that is, it hits stuff and then hits another thing and then hits another, it gets stuck in the pinball machine of the atoms, then the atoms will all start moving because they'll be absorbing the energy of the stuff moving. Yeah.
Okay. One of them they call it phlogiston. Another one was a caloric.
There's 500 ways of describing how to measure an energy unit. All right, so you can do a horsepower, you can go through all these different watts, you can go through all these different ways of measuring how much energy is in something. But the bottom line, what Newton made simple is, just ask a simple question. How much does it weigh and how much is it moving? And that's even true for heat. How much does the matter weigh and how much are the atoms moving? So you just figure out how many atoms are moving and you can figure out how much heat and how much energy the heat is.
These were words invented to try to think about energy as a thing, and it moves, and it's got to be somewhere, and so
Yes, so that's Descartes, and it's perfectly true. I don't know what piece of evidence you think makes that not true. That it seems exactly to be true. That if something moves, it took the energy from something else. That's the only way it can move, is something has to give it the energy. If something doesn't give it the milk, it doesn't have any milk. So it can be analogized. I think a fluid is a little bit too gross, in terms of, being a bigger way of explaining it than the more discrete or sensible way of describing it, as you could say, you turn into little Mexican jumping bean kind of story or some other kind of thing where you just say, look, there's this little kernel of motion in the universe, and the little kernels stick to objects. And when they stick to the object is obliged to move with some percentage of the speed of the little bits that are going the speed of light. And that works fine. It isn't challenged by any facts, okay, as an explanation. It works.
But a hot cannon had more of this in it than a cold cannon. And so you had to start somewhere. We were crawling before we even could walk. And
well, I'm just saying, it's sort of the irony is that it's an absolute truth that the cannon does have something in it when it's hot, because something has to move the atoms. All right, something has to be banging into them. So it actually does contain a radiation, and you can sit there and watch the radiation dissipate from it. You can watch it dissipate as radiation. You can put it in space, and you could actually measure the infrared radiation it will secrete.
It wasn't until we understood molecules and atoms and that we were able to say, okay, and what role friction plays in this. We were able to say, so you can store energy in different ways.
So now he's just changing the subject entirely. So he's calling it storage anytime the energy is in some discrete place, some place that we don't see very well.
And when you store it, it's not manifesting itself.
So it's always energy. So again, it's like you don't store your boat, okay, next to the riverbank and say, well, my boat has potential energy because I could put it into the river. The river's an active stream. So all of the energy is always active. And the point is you're just releasing it. So you can have a little CO2 cartridge. I mean, it's full of energy, okay? There's lots of work it can do. And frankly, it's doing work inside the container. It's busy being energetic. Okay, it's not busy not being energetic. All the little molecules have stored the pressure. They contain it. And you're just saying, I'm going to poke a hole in the balloon. It's no surprise. Pop. Yeah, not a surprise. The storage isn't dead. The storage is the same. It's energy.
It's not saying, here I am, look, it's not really doing that.
It is doing that, you just can't see it. So anything too small to see, they just say it's not doing anything. But then they know as soon as they turn on the microscope and look at pollen grains on the surface of a fluid, they'll sit there and see that the fluid's full of energy because they're bouncing all over the place. So it can be seen. We have every indication that all this is really about is, yes, we can't see electrons and protons. So when we see something that looks still, it's not still because the electrons and protons are doing stuff. Okay, they contain the temperature.
And when you're storing it, no, the object is not in motion. No, the object is not,
So again, the objects inside of the object are in motion. That's the whole point. The objects inside of the object are in motion. They are under pressure at minimum. So that's the argument, okay? I mean, clearly, if the energy is discrete little bits, and it can be excreted like a photon between objects, you could understand that could bring the objects very close, and they could be moving very little, jittering. But the fact is, there's a whole bunch of photonic type energy moving between them, reflecting back and forth.
It's not all these things that it is when it's manifesting. So let's take the simplest case. Okay.
All right, so the simplest case is that the energy really is, motion really is pressure, force. You're changing the structure of the atoms. So when you throw a wrench in space, the wrench moving in space and the wrench sitting in your hand are physically different. The one wrench has a physical difference. The atoms are in a different configuration. More specifically, the atomic nuclei are in a different configuration where their force, okay, is pointing in the direction the wrench is moving.
A roller coaster, okay?
Right.
Every roller coaster.
They're all jittering in the same direction, you could almost argue. So instead of randomly moving in all kinds of directions, jittering in all kinds of directions, the more motion you give something, the more in line the jitters are, and therefore the motion is.
First ascent is the highest.
So this is another change of subject. This isn't a very coherent description of energy, frankly, because now we're just going to talk about the stream. So there's this rain falling down, this stuff with momentum, and all you're going to really ask the question is if I throw you into the stream, will the stream push you downstream? And yes, that's what it will do.
Yeah.
Okay? So what's going on? So there you go, and you're leaning back.
You're going upstream, okay, and now there's nothing but downstream, okay, in front of you. And so now you're going to go down the stream. The stream's going to push you down the river.
And this thing cranks you up. It is endowing you with energy.
All right, so it's not endowing you with a damn thing, okay? So you're just a boat on the side of the stream. You have been endowed with nothing. And all you're really going to say is, I'm going to put the boat in the stream. And the stream goes for a little while, and then, there's rocks or there's some other thing, and so I can't go any further. There's a really low bridge, and so I can't go any further. So there's a certain amount of distance you can travel. You'll gain motion from that travel, but if you hit something, you lose all your velocity. So when you hit the low bridge, all your energy goes into the bridge. You don't have it anymore. And now the stream is still pushing on you, but you're not going anywhere. But you are putting pressure on the bridge, and the bridge is pushing you back and saying you can't go here. So it's just a stream. It's a little invisible stream of motion, and you're just going to sit there and take the motion. The motion's going to stick to you, and now you're going to have it.
Potential energy. Stored energy.
So there's no stored energy. There's no such thing. There's an active stream of gravity. And yes, when you lift something up and then let it fall, it goes downstream. That's the truth. That's how it works. That's what it's doing. That's the inverse square law. That's how it functions. And all this nonsense that there's some magic in here somewhere. No, there's no magic. There's more little particles coming from outer space than there is coming up from the bottom of the earth, and that's why you fall in gravity.
Potential gravitational energy. When you get to the top, you can calculate how, because we have formulas for this.
Oh, yeah, it's not even, you don't need a complex formula at all. I mean, this is really simple formula, actually. That's what Newton gave you, was this simple constant that basically tells you this is the rate, the exchange rate. So if there's a gravitational field, you just find out how far you are from the center, the object creating the gravity, the center of the object creating it. And if you know its mass, you can figure out how much gravitational force it's creating at different locations, and then you just figure out, simply do that. I mean, it's simple math. It's not big math. It's mechanics. It's mechanical math. Until you inject a silly squared function on time. Until you start squaring time, which makes no sense. It's not a dimensional object. You can't square it.
Calculate how much gravitational energy it handed you. So I don't feel this energy. I don't know what you're talking about.
And the only reason why you don't feel it is because it moves every part of your body. It's such as tiny, thin, little tiny bits that are hitting you. The water is so fine. It's like X-rays. It goes right through you. It just barely hits pieces of you. And it moves all of you exactly the same speed. it gives each piece, just based on how thick it is, how heavy it is, the same amount of force. So if it's heavy, it gets more force. If it's light, it gets a little bit of force. It collects it like a sail. The size of the sail decides how much wind you're going to collect. And so everything's collecting the amount needed. They all move at the same rate, and that's why you don't feel it. It's because it doesn't move one part of you more than it moves another part of you. It moves every part of you exactly the same amount, and therefore you're unaware that you're being moved. So anything that pushes you, where it pushes, each piece of skin is pushed exactly the same, then neither piece of skin can tell a difference. They can't say something happened, because nothing's happened. No skin has changed. It's only when things change the skin nerve cells can say something happened. Nerve cells can't say something happened if nothing changed between the two locations it's sensing. So gravity is discrete. It's tiny. It's a nuclear force. It's not moving you. It's moving your electrons and protons. I mean, this is the big, what physicists should be saying to people as the big reveal is that gravity is a nuclear force. It actually is not affecting you. It affects electrons and protons. It doesn't hit you. It hits your electrons and it hits your protons. It never hits you.
Until I push you over that ledge.
Right.
Over the other side of that hill. Then what?
So the obvious point is it's just about counting how wet you're getting, and then how dry you're getting when you're going back up. I mean, it's just taking away the wetness. You can just think of it in terms of you going down the stream, and then when you go upstream, you're going to have to use what you've gained in terms of velocity. You're going to have to give the velocity back. And as long as you don't give back more than you took, you'll keep moving.
What happens is your potential energy starts converting to mechanical energy, to kinetic energy.
Yeah, to nonsense energy, non-existent, unreal, fake, phony, non-Newtonian, fake energy.
It's an exact trade-off.
So the exact trade-off is momentum. That's the thing that's exact, and that's what's conserved. So you're given momentum. That's Newton's idea, momentum, not energy. And the force of gravity is whatever the amount of force is that was applied to you will change your momentum, and the two can be exchanged. You can just think of the force as an amount of momentum that you collected, and you can give back.
An exact trade-off. So all that energy they gave you at the top.
Right.
So you didn't have any energy at the top. You barely even moving at the top. You're not doing a damn thing. And it's not until you tip your nose into the stream. And the stream where there's nothing stopping you, okay? Where you're free to fall. That is, you're going to now free fall substantially. That you can gain some energy. And it really is about how much free falling you're doing, right? You have to gain it by falling the distance, okay? And you can take a longer or shorter time to do that by giving some of it to friction.
Okay? Now is return with you speeding up as you descend.
And that is
So this is like for 10-year-olds. Yeah.
when the ham sandwich
So this is they need a jokester. 10-year-olds need this jokester in the video.
becomes actual vomit.
So you're saying this is really a physics video. He's a physicist explaining energy, and we need ham sandwich vomit jokes. Fuck. I mean, I figured it was going to be stupid, clownish nonsense, but fuck. Sorry. I just hate this planet. Just hate it.
Okay.
How could that be funny to someone? I'm just please. Maybe somebody needs to explain that to me also. How could that joke be funny. I mean, I can't make it funny. I'm trying. I can't make it funny.
That's a transformation of another kind, right?
There's lots of gravity in that too, and all that kind of stuff. So blah 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 blah. You could turn it into something scientific, but why did you allow this in the first place? Why are you doing this to a physics conversation, to physics education? Why are you doing this to it?
And it's this trade-off, and it goes back and forth as you go up hills and down. If you go up a shorter hill than the first one, okay, you have enough energy to reach the top of that hill, because you started out with way more energy than that at an even higher hill. You're going to lose some energy to friction.
Right, you're going back up the stream. So you're not losing it to friction. You're you're frankly losing it because you're going back up the stream. All right, it's not the water. The friction is incidental to the fact that you're fighting the gravity, right? So it's not the friction that stops the rocket from going faster and faster. It's the fact that it is fighting the gravity. It's not just the atmosphere. The gravity's stopping it.
Okay? So, in other words, you can't ascend back to a hill exactly the same height that you started at.
Well, there you go. But yes, you can. It just requires you to be on an air track or to be on some mechanism where you can effectively make friction irrelevant.
Okay, some energy will go to friction. And when you lose energy to friction?
So those are two different things. He was talking first about going up a lesser hill, all right, when you have more energy already collected. All right, now he's talking about just going straight back up the same height you had. And theoretically, that is doable.
That makes heat. Okay? That's the source of heat when you lose energy.
So the source of heat it takes a portion of your momentum. So he's not saying the word momentum, but yes, you can't make heat unless you're taking momentum. And if you're taking the momentum and you conserve momentum and yet you lose kinetic energy, you can't use some silly argument that I lost the kinetic energy but I kept all the momentum. You can't do that. You can't blame heat if what you're trying to explain is where you perfectly conserved momentum and yet lost kinetic energy. So every time you lose kinetic energy and conserve the momentum, you can't use heat as an excuse.
All right. So that's why the engine of your car gets hot.
Right.
Okay? Not all the energy that you started with got transferred to the motion of the car. The losses went to friction. The friction heated your engine.
It's just like the cannon. I mean, the problem is there's no way to fix the fact that the explosion doesn't happen in one direction. So every time the cylinder has an explosion, a substantial portion of the heat and the energy of the explosion is going the other way. It's not going the way of the piston. It's not just pushing the piston, it's pushing all the other metal, and the push is substantially high thermodynamic pressure.
Your engine gets hot. Okay. So in a roller coaster, you're converting gravitational potential energy to kinetic energy and back and forth and back and forth.
So you're not converting anything, you're just going upstream, downstream, downstream, and you can go a little bit upstream, but if you go too far upstream, then you lose all your energy and you're stuck on the shore. Blah, blah, blah.
Back and forth. And if they designed it right, the frictional energy that you lose, okay, you don't go up higher and higher. The hills you go over have to get lower and lower, and there's the last one that you come in for the stop.
Right.
So they gave you the energy when you started at the top of that hill. So that's gravitational potential energy becoming kinetic energy.
And it's just wrong to say it that way. Gravity is an active field of energy, and all you're doing is dipping your toe in it, and then pulling your toe out, and then dipping your toe in it, and pulling your toe out. You're just basically, it's a sail, and there's a wind machine, a fan, and you're basically just saying, I'm going to turn my sail against the wind, and then I can turn it so I don't get any wind, and then I can turn it on, I can turn it off.
That's what's going on there. And like I said, if you go back up a shorter hill, you'll slow down because some of that kinetic energy is giving back to you, so you can have another little lump of potential energy to take the next hill that comes after that.
God, this is so. Who is this for?
All right, so that's easy. We've had roller coasters forever. You can have imagined them forever ago. But it's more complicated, or a little more physics involved, if you want to say, this molecule has energy. A molecule. Well, how am I going to get the energy out of the molecule? Just sitting there.
Well, that's an atom, but whatever. Yeah, looks like an atom, frankly. Doesn't look like a molecule, but whatever.
Oh, well, you can...
In my opinion, you could just say these are electrons, blah, 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 blah. The bonds are really close to the other object. It's shared electrons, blah, blah, blah. You know, this isn't really a very good model. Let me just say that. Atoms aren't perfectly round. This is another thing to say.
In one case, burn it. Burn the molecule, okay? Why is it that you can throw a log in the fire?
So burning the molecule isn't a very good way to say it either, right? You're really just saying that when you take a complex arrangement of atoms that are glued to each other based on sharing electrons, that when you break it apart, there's pieces left over. And that's the simple thing to say. So you break it into two pieces, and there are little bits that fly off because they're leftover bits. You lose some of the pressure that was contained in the bigger object. And that whatever you're losing becomes the mechanism to sustain the flame.
And the log is room temperature. You put in the fire, then the fire ignites the log, and the log keeps burning. There's chemical potential energy in the molecules of the log.
All right, so again, this potential thing again, it's real energy contained in the bonds between the electrons and protons. It's real. And you're basically pulling magnets apart, you could argue. And when you pull them apart, you understand that you're losing little pieces, and those little pieces fly off at potentially high velocities.
Where did that energy come from? Where did the log get that energy?
Gravity. So gravity is the big source of all of this stuff, because gravity tends to push stuff together. So it's the first source of storing energy.
Energy, Chuck. You tell me right now.
The log, it's from its molecules. It was storing.
Where did its molecules get their energy?
Inside a sun is where he's going eventually. So the pressure inside of a sun is where these pieces are put together in these geometric shapes that allow their tensions and attractions, their attractions and repulsions to balance. And there's only 100 or so of these configurations, geometry, that actually are sustainable, that'll stay together. All the other configurations fall apart. That's why there's only 100 elements to start with, is because the geometry is very strict in terms of creating a balance between the pressures. But there's a lot of pressure because that was formed inside of something that was intensely hot, and the pressure was intensely high, which meant there's a whole bunch of energy from the outside pushing the little bits closer to each other than they wanted to be. Closer to each other than they would be if they were in free space. So by smashing them close to each other, you can force them to live with each other.
Okay, let me think about this. From their atoms?
What did the log used to be?
Oh, that's funny.
No, it used to be a tree.
A tree. How does a tree get energy?
From the sun.
Thank you. So the sun builds molecules that contain stored energy, So that
So again, stored energy. The molecules contain them. The ones that started it are the ones being pushed together. No, the point is that they take molecules that won't stick together and they force them together. They apply enough energy to force the pressure to be part of the new thing you made. So you have to overcome the resistance of the molecules to be put together. So the tree is forcing them together using the sun's energy.
that's why wood burns, because it has stored chemical energy given to it by the sun.
It has stored pressure. Is probably a more sensible thing to say. Atoms store pressure. And the bigger the atom, the more pressure it can store. You can sort of understand, and that's when you start getting into the whole nuclear thing, where you can cause a chain reaction.
Sun.
Look at that.
And it's just sitting there minding its own business. But that's why fires in homes are so deadly, because there's all this potential energy stored in the molecules of organic matter, wood.
All right, so that's even almost silly. I mean, a lot of homes now are dangerous because the house is made out of chemicals, not wood. But whatever. It's glued together.
If your house is made of wood, so that the whole thing burns, converting the chemical energy into thermal energy. So much of our lives is the conversion of energy of one form into another. And what happens while...
So there's only one form of energy, and it's this little crap moving the speed of light that moves electrons and protons. So the forces that move you are, the same forces that are moving electricity, moving electrons from one atom to another atom. It's all the same. That's the energy. There's not different forms of energy. There's only one form of energy, and that is the bits, the force that sticks to electrons and protons. They have to do it all first. Nothing happens till they get moved, and they get moved by the little bits of force, nothing else. You can't move electrons and protons with something other than the forces between them.
That's going on. So other forms of energy. There's energy in the nucleus of an atom.
Yes.
You split the nucleus and take it out. We make bombs doing that. Okay?
It's the same difference, really. Okay, so yes, breaking an atom, breaking molecules apart, you're releasing little extra bits, and the same thing happens when you break a nucleus and create two new atoms. There's a bunch of leftover bits, and the leftover bits break other atoms, and that's your chain reaction.
So we turn nuclear energy into the kinetic energy of an explosion.
So the kinetic energy meaning what? The mv squared, that means little bits have more energy, more power than big bits?
To do damage to things in warfare. Okay?
I take 100 atoms, 1,000 atoms going 1 mile an hour somehow, has 1,000 times less energy than one atom going 1,000 miles an hour. It can move more, it can do more work. No evidence that that's true. And Newton certainly didn't believe it was true.
That's nuclear or chemical energy. Some chemicals will give you their energy not slowly, like a slowly burning log. They'll give it to you catastrophically. All right? And we call those bombs.
Fast. Catastrophically. They give it to you fast.
Okay? Or a firecracker. Catastrophically. Boom!
Fast. Fast. Not catastrophic. Just fast.
The energy goes to break apart the firecracker, goes into the sound that it makes, the shock wave, all of that. So our lives and everything we do is nothing but a ballet of the conversion of energy from one form.
Okay, it's an exchange of energy. So there's no real conversion. There's nothing, it's all heat. I could throw this, and it'll move in a direction. And the reason why it's going to move is going to be the same as if it was heat, except the heat's just moving in one direction. So it's almost thinking about light. I can have a light bulb and I can have photons going in all directions. Or I can have a laser beam and I can have the light go in one direction. It's all the same thing. It's all just photons. So in a sense, the argument is that if you understood that there can be pieces of a photon, parts of a photon, then you could understand that that's what energy is in the universe. It can be in the form of a photon, or it could be in the pieces that make a photon.
Into another. Do you know what the French word is for energy?
I do not.
They didn't invent the word energy until 1830 in terms of using it like it was a word. Okay. It's a similar story to like photon. It wasn't used as a word until like 100. A little bit before Einstein.
Calorie.
Oh.
Okay.
Leave it to the French. Calorie.
Okay.
With the cause.
So when we consume food that has calories,
Right, they called it caloric. Okay, so so in the 1800s they called energy caloric. They didn't call it energy. And before that they called it quantity of motion. So what? It's the same thing.
a 1-for-1 definition of calorie is energy.
But what does not have calories, of course, are cigarettes. Which is why we smoke them. Because they are not fattening and they make you look so cool.
So the video is basically made for a 10-year-old, and then he's going to talk about smoking.
Fuck. Thanks for that 1950.
Yeah, commercial for cigarettes. Brilliant. Shit. God, I hate this planet.
He's referenced to
Of course.
cinema. French cinema.
I know.
So,
I have to go take a faint. I can't. I can't do it. I just don't. I don't know how I'm going to endeavor to persevere and get to the last choking moments of my shitty life. Just don't know how I'm going to survive surviving. Oh, fuck. All right, I've regained my strength. So move along.
but think about it. So you eat food that has, you look at the calorie content. That's how much energy it has. Okay? So then...
Available energy, without nuking it. Okay, so that's the stuff you can get from it, by just breaking the atoms apart, changing them from one form to another.
You consume it, you need energy to live, to move, your heart beats. All this requires energy. You're getting it from the calories of the food you eat.
The calories basically measured in the sugar content of the, acids and bases, or, so I mean, it's all kind of a narrow description of the absolute energy. It's the available to a human digestive system, you could almost argue. It's not the energy.
So what happens if you consume more calories than you need? Your body says, store that. So it creates chemical potential energy in the form of fat. And it stores it away.
I'm not fat. I'm just filled with potential. What you talking about? You see this? This is potential. I am potentially Michael B. Jordan. I am potentially Michael B. Jordan. That's
Yeah, it's just a knife in my brain. Oh, okay.
what the potential.
My six-pack is just beneath the potential.
It's just
Right,
beneath
that's right,
all
you
this
got it.
potential. You don't even know what you can have.
And by the way, that conversion of your body's calories to your energy is not perfectly efficient. So what happens to
Yeah, so the whole thing is kind of a lie anyway, right? I mean, yeah, you don't metabolize all the calories in the substance, so it depends on really what the substance is. So if it's a piece of bread, you're going to get all of the calories. Your body's going to take all 250 or whatever the number is. But if it's some beef burger or something, your body's going to say, I don't want to have anything to do with this shit, and it's going to get rid of it. Uh,
that excess energy that's not converted? That's the inefficiency of your body. We're an engine of sorts. It's inefficient, so that inefficiency gets converted to heat.
all right, so it's almost silly, right, for somebody to say that the body is inefficient when we can live on almost nothing. I mean, it's amazing how much we get out of so little. So that part's a little bit ridiculous.
So your body heats up when you exercise. It's a consequence of the inefficiency of your body.
No, well, that's again more kind of garbage. I mean, it's not. Our bodies are really efficient compared to any hydraulic system we make or any other kind of system we make. They lose even more, in a lot of cases. So again, I don't think this is. I mean, I don't even know why he's going here to point out the gross inefficiencies of biological organisms when now nature's really squeezed almost everything out of them.
But your body loves that because now it's part of your temperature regulating system. But I'm just saying, when you exercise, your body heats up. In the same way you drive a car, the car heats up. In the same way, the wheels and the tracks of a roller coaster are actually getting hot because of the inefficiencies of the conversion, because there's inefficiencies in every conversion of energy from one.
All right, so there isn't any inefficiencies in these chemical conversions, though. So there's no friction between electrons and protons. There's none of that. It's all clean force interactions, and there is no waste.
Form to another.
There's no inadvertent heat or some other kind of word you want to use. It's all on purpose.
So the only point of this explainer is,
I guess the point is we just call work we didn't intend or work we can't use. We just call it waste or heat or some kind of bullshit when no, it's part of the process.
just to say, so much of what we do and how we live involves the clever conversion of energy from one form to another.
So it's not about converting it from one form to another, and the simple example is the 5-ton train. Add 5 tons to it, it becomes a 10-ton train at half the velocity. The momentum is perfectly conserved, but you lose half the kinetic energy. So half of their mathematical notion of reality that isn't Newton's physics disappears, and it really can't be accounted for. Because if you made heat, then you wouldn't have the same momentum. You can't conserve the momentum and make heat.
Nuclear energy, chemical energy, which is molecular. We have kinetic energy, gravitational energy.
Yeah, so it's all just force being converted into small bits moving fast, converting into big things moving slow. Or big things moving slow, converting into little things moving fast. There isn't anything else happening.
All of this comes together, and our ability to exploit that in the service of civilization is one of the great triumphs of physics.
All right, so this is another joke. So it's a great triumph of physics that you're on the brink of creating a global weather catastrophe. In which millions of people will have their lives ruined and be probably killed, frankly. Tsunami to death. Yeah, that's a brilliant achievement.
Especially 19th century physics, where they figured out,
Yeah, when they figured out how to drop bombs on civilians, I mean, where they deliberately did collateral damage. I mean, the Japanese, when they attacked Pearl Harbor, they didn't like blow up people's houses. They didn't go say, let's go find some civilians to kill. It's just pathetic. Our triumphs.
My gosh, look what we can do. Another quick one, just look at a locomotive, right? Well, what's going on there? Well, the locomotive, all right, I don't know if you remember, they'd have to fill up from water tanks every now and then. Okay, well, what does the water do? Well, a locomotive burns either coal or wood, and it heats so that's the chemical energy. It heats a vat of water, so it's got the stored chemical energy of the wood into the active thermal energy of the vibrating water molecules. They then evaporate, creating pressure for the steam
Well, it's both ways. The steam engine's using both sides of it's creating the pressure to move the cylinder, and then it's creating a lack of pressure, of vacuum, to move the cylinder. So it's doing it on both cycles. It's taking advantage of both heat cycles.
Wheels to have the locomotive go forward. Oh my gosh. And that all started with solar energy that made the wood or the coal, that made the fire, that made the boiling water, that made the pressure that moved the wheels. All of this.
Yes, it's all solar energy. Oil is solar energy. It's just a few 100,000 years of it.
Is a triumph of our understanding of energy.
Now, what you just said there, I can hear Exxon going, listen, guys, we're actually solar energy. Okay? So,
Yeah, and it's actually true. It doesn't change the fact that it's dirty, but I mean, the fact is it's incredibly compressed solar energy. Tons and tons and tons and tons of wood, okay, reduced to a little ounce of fluid.
I just see it coming
Ultimately,
down. Ultimately,
it started
guys,
as solar energy.
this is solar energy, okay?
Fossil fuels started as solar energy. This is true.
Damn.
This is true. It reminds me, and we got to end right now. It reminds me of this bumper sticker. It says "No nukes," right? From the anti-nuke movement, and then the O in the "no" is an image of the sun. It says "No nukes."
No nukes. Okay, yeah, exactly.
Well, I know what they mean. They want you to use solar energy, but the sun makes its energy with nukes. All right, just like make that clear here. That's how it started that way. So, and
Yeah, and it's a million. Yeah, so I'm all for nuclear power plants if you can put it 1,000,000 miles away. Yeah, go ahead, build lots of them. So if you want to put a nuclear power plant on Mars or something, yeah, go ahead. You have my approval. Fuck. I don't want it in my backyard, though. You want to live next to it? Let's put the transmission lines right over your house. And then you can explain how, well, it's all harmless.
anyhow, I just thought I'd put all that out there, and so just to enhance our appreciation for what energy does for us.
So it enhanced my realization that the world is just so fucked because this is what amounts to intelligent conversation. Fuck.
And how being clever has enabled us to build civilization.
Oh, again, yeah, in the worst, sloppiest, messiest, crappiest, shittiest way possible. Leave most people poor and utilized. Okay, let's not dare try to maximize our productivity as a civilization.
Of converting energy from one form into another.
Right, so you're not doing that. You're just converting it from one place to another. That's what you're really doing. Energy just moves things. So you're just moving stuff from one place to another. The force is going places anyway. It's always going the speed of light, traveling through the universe. And all you can do is make it push something for a while. And that's all energy is. It starts with the little bits, photon type objects, and it ends in, skyscrapers wobbling.
Yeah, it has built civilization, and ultimately it will destroy civilization.
Destroy. On that happy note, Chuck, thank you. This is
So it's not going to be such a laugh, when it happens to you. He probably has a beach house somewhere.
been another Star Talk explainer. This one on all forms of energy and how it can create and destroy all that we.
Blah, 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 blah. So he didn't really get to the subject of energy, which is the big point. The big takeaway, again, is that there's only so much energy in the universe. And all you're really going to do is say, where is it? Is it moving little things, moving big things? Where is it? But it's always the same amount. Every second that ticks by, there's always the same amount of energy in the universe. All right. Excluding the photons, yeah, they just keep going. I think they bounce back. I think that's the trick. The universe is a bubble, and nothing escapes. All right. Anyway, enough. It was surprisingly juvenile and thin as science. I knew it was going to be bad, but I didn't think it would be this bad. All right. So, till the next time and such, this has been a draftphysics.com, debatephysics.com, but nobody's capable of doing any of that. Video presentation. Till the next time and such.